So this is stresses placed on a system that is in chemical equilibrium. The last video we did together, we discussed what equilibrium was. So a brief review of what equilibrium is. Remember, equilibrium means that the rate of the forward reaction is equal to the rate of the reverse reaction, and you need two prerequisites for that to occur. You need a totally closed system so you don't gain or lose any products or reactants, and you need the products to be totally saturated. When that occurs, then the arrows can be both ways. Remember, equilibrium does not mean that the concentration of the reactants is equal to the concentration of the products. That's not what it means. So we're going to go over certain types of stresses that we're going to put on an equilibrium, and it will shift a little bit, but it will eventually go back to the same products reactants ratio. So what we're going to discuss today for the stresses: concentration is a stress, temperature is a stress, pressure is a stress, and we will go over how a catalyst would be a stress on a system at equilibrium. So the first thing we're going to go is the effect of concentration on a system at equilibrium. This is the chemical equation for the formation of ammonia. Now notice an arrow going forward and an arrow going reverse. That means that this system is at equilibrium. So going this way is synthesis of ammonia. Going this way would be decomposition of ammonia. So what we're going to do is we're going to do this first. We're going to be using that equation for almost all the stresses. So for letter A, we are going to increase the concentration of H2 gas. So in other words, what we're going to do is if we increase the amount of H2 gas, what's going to really happen is there will be more collisions with N2. And if there's more collisions with N2, that will make the reaction fire forward. The reaction will fire forward, and what happens is this: once the reaction fires forward, let's say we double the amount of H2 from 3 moles to 6 moles. So more collisions, the reaction fires that way. It's going to take N2 with it, so the concentration of N2 will go down. And since it's firing toward ammonia, the production of ammonia will go up. Now, interesting part. Since instead of having 3 molecules or moles of hydrogen, I doubled that, this reaction will fire toward the products until the products double. In other words, until this 2 goes to a 4. Once the products double, then the reaction will go reverse again, and we will have equilibrium once again. And this number will be 6, this number will be 4, but if you look at it, the ratio will be the same. So when you put a stress on a system at equilibrium, it'll fire either to the right or to the left for a while, but then it will eventually settle down and be the same or the constant ratio between the reactants and the products. So that's what happens when I increase the concentration of H2. So now let's do this. For letter B, we're going to decrease the concentration of N2. So if I decrease the concentration of N2, let's say I cut this in half, what will happen is this reaction will try to fill the void. So the reaction is going to fire this way, and since I cut that in half, this reaction will fire this way until NH3 goes from 2 to 1, and it keeps the same ratio. But let's see what happens to the other substances. If the reaction is firing to the left, obviously the NH3 is decreasing. And if it's breaking apart this way, the N's are going to start filling up the N's where we took them out, and the H's is going to start to increase. So we have an increase in H2. So that's what would happen if we took out some N2, the reaction would fire to the left. Okay? So for letter C, we're going to decrease the concentration of ammonia. So we have decreased that concentration of ammonia, so the reaction will fire to the right to make more ammonia, or in other words, the ammonia that we lost. So as the reaction fires to the right, we are going to decrease both N2 and H2. So decrease in N2, a decrease in H2. I tell my students for concentration, I always tell them about mound and hole. If I take out some product or reactant, that's a hole, you got to fill it in. If I add some concentration, that's a mound, and it's got to be swept away. So here, if I took out NH3, that's a hole, we have to fill it in, so the reaction will fire toward the hole. Okay? Now, let's do this. Letter D. I'm going to increase the concentration of N2. When I tell my students, if I increase the concentration of N2, that's a mound. And the reaction will always fire away from the mound to make the playing field all level. You don't want any mounds, you don't want any holes. So, increased concentration of N2, that's a mound. We're going to sweep it that way, so the reaction fires that way. H2 will be swept to the other side, though that'll go down. And NH3 will go up. Now, don't forget, this stress is just temporary. So if I change that one molecule to two molecules, the reaction will fire until that goes to double or four, and then it will go back. Remember, in equilibrium, the rates of the forward and reverse reaction are always constant, and the ratio between the reactants and products, it's always constant. All right? It's a stress, and the stress stresses out the system for just a little while, and then it'll go back to equilibrium. So that is how the effect of concentration stresses out a system in equilibrium. The next one we're going to do is how temperature stresses the system in equilibrium. So like I said, we're going to use the same equation, the formation or the decomposition of ammonia. And for the second stress, the effect of temperature on a system at EQ. So what you have to do is you have to locate where the energy is. Is the energy with the reactants or is it with the products? Okay? Energy is, in these reactions, is like heat energy or temperature. So for letter A, if I increase the temp, that means I'm going to increase the energy. And if I increase the energy, that's kind of like the mound and hole thing. If I increase the energy, which is right there, that's going to be a mound, and we have to sweep the mound away. Okay, so whatever side the energy's on, if I increase it, it's going to go away from that energy. So in this case, if I increase the temperature, there's energy. The reaction will fire this way. It'll fire this way. And what'll happen? NH3 will decrease. H2 and N2 will increase. And there's something else very interesting. If I increase the temperature, the reaction will go away from the energy. And if you look, this way is an endothermic reaction. So an increase in temperature favors an endothermic reaction a little bit more than an exo. So for asterisk, increased temp an increased temp favors an endothermic reaction. Okay, and remember, if the temperature's increased, the reaction will fire away from where the energy is located. So, if you know increase in temp, then obviously you're going to know a decrease in temp, and that'll be our second and final one for temperature. So, we have a decrease in temperature. A decrease in temperature, you got to find out what side energy's on, and that means you're taking energy out. Remember, you have to have a level playing field for this equilibrium. So, if I take that energy out, that is, remember we talked about mound and hole, that would be a hole. You got to fire toward the hole to fill it up. That's what we're talking about. So, if there's a decrease in temperature, that means there's a decrease in energy. The reaction will fire that way. And what will happen is N2 and H2 will both decrease. NH3 will increase. And if there's a decrease in temperature, look at, if it's going this way and the energy's with the products, that means it's going to favor an exothermic reaction. So a decrease in temp favors an exo reaction. Decrease in temperature favors an exothermic reaction. So, you know, for these stresses, it's all about molecular collisions, but for concentration as a stress and temperature as a stress, you can think about mound and hole. Remember, if it's a mound, you've increased something, it's being swept away from the mound. If it's a hole, you have to fill in the hole, it's got to go, the reaction has to go toward the hole, okay? Those are the only two things you can use mound and hole for. Now, the next stress is a little bit more difficult, and that's pressure. Pressure is a very interesting stress on a system in equilibrium. Notice that this system, gas, 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 is an all-gas system. And yes, pressure will definitely affect that system. Now, remember, pressure doesn't affect solids or liquids. But if it's an all-gas system, pressure will affect it, and what we're going to talk about will work with it. If it's not an all-gas system and it does have a gas somewhere, that's a different story. So, remember, pressure always goes from high to low, right? Pressure always goes from high to low. So, in a plane, if the plane goes up in the atmosphere, there's hardly any pressure outside the plane. If a window blew out, the pressure would go from high pressure inside the plane to low pressure outside the plane. If you're in a submarine, there's a great amount of pressure outside the sub, less pressure inside, so the pressure would go from high pressure from the water into the sub, which is low pressure, okay? So an increase in pressure always goes from high to low. But how do you know what's high and what's low in an equation? It's a good part. So for letter A, we're going to increase the pressure on that system. This is how you tell what side's high and what side's low. You look at the coefficients. There's 1 there, there's 3 there, so the coefficients on the reactant side is 4, there's 2 there. If I'm going to increase the pressure, pressure always moves from high to low, so it would go from 4 to 2. Remember, increase in pressure always goes from high to low. So if it's firing this way, we know that N2 and H2 will decrease. And we know that NH3 will increase. So just remember, an increase in pressure always goes from high to low, and if it's an all-gas system, you just count the number of coefficients, and that'll tell you. So, for letter B, obviously, if there's a decrease in pressure, and this is 4 to 2, you would go the opposite way. A decrease in pressure goes from low to high. Most of the time, it will be an increase in pressure that you'll be talking about. Okay? So for an all-gas system, you can count the coefficients to see which way the pressure is going to go. Okay? But for letter C, I'll give you a different equation. So here's H2 plus I2 yields 2HI. And we have H2 as a gas, I2 as a gas, and HI as a gas. Okay? So I'm going to increase the pressure. Since it's an all-gas system, we can use the coefficients. So look. There's 1 there and 1 there, so that's 2 on the left-hand side. But look over here, there's 2 here. So there is no high or low. So if the coefficients on both sides equal each other, pressure has no effect. Okay? If they're equal to each other. Now, next question, what if it's not an all-gas system? Well, I'll give you the classic example of that right now. All right, now, I have CO2 solid is in equilibrium with CO2 gas. It's not an all-gas system, so we can't use the coefficients. But here's a little rule. I'm going to increase the pressure. If you increase the pressure on a system that's not all gas, look for what side has only gas on it, all right? And an increase in pressure will squeeze that gas into a liquid or solid. So my rule is, if it's not an all-gas system and the pressure's increased, the reaction will always fire away from the gas. So if you look up here, there's the gas. An increase in pressure will squeeze the gas into a solid, so the reaction will fire away from the gas toward the solid. That's a trick question. Just remember, if it's not an all-gas system, the reaction will fire away from the gas if the pressure is increased. So now we've gone over effective concentration on a system at equilibrium, effective temperature on a system at equilibrium, effective pressure on a system of equilibrium, and the last one is the easiest one, the effect of a catalyst on a system at equilibrium. So, fourth and final stress that we're going to do today on a system at equilibrium, the effect of a catalyst on a system at equilibrium. Now, you got to remember one thing before we even think about putting this in and how it affects a system at equilibrium. A catalyst lowers the activation energy. So, you got to remember, a catalyst lowers the activation energy. Remember activation energy? It's used to break the old bonds before you can make the new ones. So, lowers the activation energy of a chemical reaction and makes the reaction faster. So, the easy thing about a catalyst is, if you put a catalyst in a system at equilibrium, it speeds up both the forward and the reverse reaction the same. So it speeds up both forward and reverse reactions equally. And that's what you have to remember about a catalyst. Speeds both reactions up, forward and reverse, equally. So those are the stresses that we have for high school chemistry. And don't forget, when you put a stress on a system at equilibrium, it will fire either toward the products or toward the reactants, but it won't do that forever. It will eventually go back to equilibrium and have the same ratio between the reactants and the products. Okay? Hope you understood this one.